So Atwood machines they're classic physics questions, and they make up one of the backbones of kind of like what you should expect in your test kind of problem. So this one is considered the modified Atwood machine because only one of the two masses is actually determining the determining the net force on the system. So the modified Atwood machine has a block or a mass on the table, frictionless or non-frictionless, doesn't matter, it's still considered Atwood machine, and has a second block that's hanging. And as the year progresses, how we determine this problem is going to change. We will start these problems where the mass of the pulley is 0. So the inertia of the pulley doesn't contribute to the problem. But we won't be doing that for very long. So once we get in the second semester, our pulleys will have inertia, and therefore they will affect the problem. But this is considered the classic modified Atwood machine question. So the first thing I need you to understand before we even get started with this is that most pulleys in general don't do much more than redirect force. Although we talked about more complicated pulley arrangements, most of the time in a problem like this, if you see a pulley, it's just going to redirect the direction of a force. However, in all problems, what you should be doing is recognizing that Newton's third law is actively playing a role in the problem. And Newton's third law merely states, and I know I said this yesterday, I'm reiterating it, that for every force, there's an equal and opposite reactive force. That's Newton's third law. For every force, there's an equal and opposite reactive force. Sometimes that force, the reactive force, isn't part of your problem. For example, if I was to ask you what force is acting on the block that is hanging, could you name one? Name me one of the forces acting on the block that's hanging. So the weight is the force of gravity, which means that somewhere there, that's what you guys want, right? There. That make it a little bit easier? The worst thing is, not only did I not put it up on the screen, and you guys didn't say anything. That was very nice of you.
I thought you knew. I didn't want to say something.
But the other part is, although I started recording on my iPad, I didn't start recording on the computer here. So the thing I've been trying to do is record on the computer because
this meeting is being recorded.
Because I really love hearing that voice. But also because it tends to be a little bit more complete. I keep forgetting to hit the start button here on the iPad. So this again is the modified Atwood machine, blah, blah, blah. You get that point. But let's start with the idea of Newton's third law, that for every force there's an equal and opposite reactive force. Sometimes that force is actually a part of our system. A lot of times it's not. So when we talk about the weight here, this is the force of gravity acting on a block that is hanging. There is an equal and opposite reactive force. And that force acts on the earth, pulling it upwards. I don't really have to worry about that force. It's not a part of this problem, nor is it going to affect the actions of this problem. So in that case, the reactive force doesn't enter into this problem at all. On the other hand, there's another force acting on the system, acting on this weight. What's the other force that's acting on this weight? So there's an upward tension force, sure, which I'm going to currently label T1. So there is an equal and opposite reactive force. And that force acts on the pulley here. That is also T1. It is the equal and opposite reactive force. It is a part of my system. And I do have to keep it in mind, and I do have to consider it. Because it's acting within the realm of how it influences other objects in the system. So although I've covered all the forces acting on the block that's hanging, the fact that it's hanging causes tension in the cable. And because of that, the tension in the cable is going to influence what's happening to this block. Now, Atwood machines are actually classic machines that are about inertia. They're demonstrating that the inertia of the system is separate from the gravitational force. That's what the Atwood machine is about. So if you don't appreciate that, please understand in your notes that we are going to see the force of gravity act on this object as the external force, but the acceleration of the system will be based on the system's inertia. That's our expectation. Anybody from AP Physics 1 should remember that. So I'm going to go further, but at this point, I've covered all the forces acting on the block that's hanging and one of the many forces that's acting on the pulley. So let's go to the block that's on the table, talk about the forces acting on it. So would somebody be so kind as to name one of the forces acting on the block on the table? So we have a normal force. Now, by drawing that right where I did, I really left myself open to a problem. So I'm going to put this over here. There's a normal force on the block on the table. Yep. So the Newton's third law force is the one that acts on the table from the block, which means on the table there must be a downward normal force. But this force acts on the table, it doesn't act on the block. This becomes an issue when I have one block stacked on top of another block, which we will see in short order. Now, there is, of course, the weight. I'm going to take that one from you guys, which I know is balanced by the normal force here. But the Newton's third law force, again, would be another upward force on the Earth, and I probably can ignore that. But there is a cable connected to it, so I do have to consider the fact that there's tension here, T2. And the third law reactive force is the force of tension that acts on the pulley, where the other end of the cable is attached. Now, T1 does not have to equal T2. And we're going to get to a point where we will never assume that those are equal. The only way they would be equal is if the pulley itself didn't have any inertia. If the pulley has inertia, then it has to take an unbalanced force to get it to turn. In this case, an unbalanced torque. But if there's no inertia with the pulley, then it doesn't take any unbalanced torque to turn, and therefore T1 and T2 would be equal. But I don't want you to assume it. In your notes, I want to make it clear. We will, for the time being, to make our problems a little simpler, have these massless pulleys. But that's not going to last very long. So don't always assume the two tensions are equal. Consider why it wouldn't be equal before you assume it is. But for our problem now, to simplify it, we're going to say it's a massless pulley, which will make T1 and T2 the same magnitude. All right? Now, to fulfill this problem, I'm going to give a couple of things here, M1, M2. That way we can differentiate them. And what I'd like to do is I'd like to find the acceleration of the system based on what we are seeing in our problem. That's a pretty typical thing to do. These problems are, again, classic Atwood machine questions where ultimately we are looking for the acceleration of the system. And I want to be very obvious about this. We should have an expected outcome that shows that the acceleration of the system is based on the inertia of the system. So we are looking for somewhere towards the end of the problem, some case where the entire inertia of the system, M1 plus M2, is acting to determine the acceleration. That's what we should expect to see. However, we are still going to analyze these questions the same way we analyzed our single body problems. That's what this is about. It's about showing that whether it's a multi-body problem or a single body problem, the analysis is the same. So, enjoying lunch. So we're going to start by recognizing that the block that's on the table is experiencing, although three forces, only one of them matters, and this is the force that's horizontal. The only time these vertical forces would matter is if the table has friction. So the net force in the x direction is going to be M2A, because that's the one that's on the table. There's only one force causing that, tension. The biggest mistake is to assume the tension would be the weight of the hanging block, and it's not. The tension in the cable is going to be less than the weight of the hanging block. It has to be. The only way the hanging block accelerates downwards is if the forces on it are unbalanced. So the upward tension in that cable has to be less than that block's weight. So we can't assume that this is the weight of the block. But this is as far as we can get in analyzing the forces acting on the block on the table. So then we take a look at the block that's hanging and recognize it's got, again, two forces acting, tension and weight. But the weight on the table is, the weight hanging is M1G. Now, it's at this moment that I really need to pay particular attention to direction. I made this direction positive for the block on the table. In order for you to have consistency in doing these problems, I would encourage you to indicate a direction for the problem that is common to both parts. This is not how your textbook does it, by the way. Your textbook does this different, and so if you want an alternative, look at the way the textbook does it. I tend to be a pragmatist, which is make your direction something that is intentional. The book, it divides the problems up into pluses and minuses that same way every time and employs a different principle in order to determine direction. I don't particularly like it, but if you want an alternative, look at the way the book does a problem like this. It might favor your way of thinking. But because I'm trying to be intentional, I'm saying that if the block on the table moves to the right, the block that's hanging has to go downwards. Since there's no alternative to that, I'm going to make to the right positive for the table and downwards positive for the block that's hanging so that they agree. So over here I will get M1G minus tension equals M1A. When you're done, you should get a group of relationships. It won't necessarily be two. You can have up to two relationships for every mass in your system. An X direction and a Y direction, all around. But you should be left with something that you should be able to combine for the system. Our system has a common acceleration. So what I'd like to do is find out what the acceleration of the system is. This means eliminating the tension. And although there are a variety of ways to do that, substitution is what I'm going to jump to. So I'm going to make the substitution. Pretty straightforward substitution here, I think. And to finish out the problem, I want to get A by itself. Before I finish, I do want to point out that this is exactly what I was hoping to get. I was hoping to see that this side, I have the unbalanced force that caused the motion of the system, the hanging box. On this side, I have the entire inertia of the system. And here I have the acceleration of that system. In any one of these multi-body problems, you should at some point in the problem see the representation of Newton's second law. The unbalanced force equals the inertia times the acceleration. It should show up. You know you kind of done it right if the inertia of the system shows up somewhere. So if you have three objects that are linked together, at some point you should see M1 plus M2 plus M3. Their inertia should always show up in the problem somewhere. So either way, the actual answer to this question, if you were asked to find the acceleration, looks something like this. It is pretty traditional to group the mass part together. The biggest takeaway, that's although mathematical, but the biggest takeaway here is that no matter what you hang, the system accelerates. There's no way you can say that, well, the block on the table is too big for the system to accelerate. If there's no friction, the system accelerates, period. The only way for it not to accelerate is if the mass on the table is 0 or the total mass in the bottom is infinite. So it's going to accelerate even a small amount. It should also be clear that if the mass on the table is 0, then this block falls with just the acceleration of gravity, meaning if I cut the string, it falls at g. I should expect that too. And that's what happens here. If m2 is 0, I get m1 divided by m1, so the acceleration equals g. This is the most straightforward multi-body problem that there is. Again, throughout the course of the day, I'm going to be doing 3 of them. 6 periods getting the standard Atwood machine, and 7th period is getting the train problem, where one box is pulling another box, which is pulling another box. So there we go. And we did this one in 4th period. So modified Atwood machine, box on the table, box hanging off the side. We will also have this point where we see the total mass show up. In all of these multi-body problems, we expect the inertia of the system to make an appearance somewhere. All right, so here we go. This is the standard Atwood machine, which is just 2 boxes on a pulley. So I'm going to mount the pulley to the ceiling because we're going to take a look at several parts of this problem. And I'm going to hang one object on this side. No, I'm not. Yes, I am. And I'm going to hang one object on the other side. Generally with an Atwood machine, there's quite a few things you can do with an Atwood machine, but they are traditionally used for force discussions and energy discussions in physics. So 2 objects hung on the pulley. Now, this is supposed to be a discussion about Newton's 3rd law, and that's where multi-body problems really stem from. And Newton's 3rd law, we need to establish, has 2 real parts to it that are important. First, there's the actual law, which is about forces. The idea that for every force, there's an equal and opposite reactive force. That's Newton's 3rd law. For every force, there's an equal and opposite reactive force. It's not for every action, there's an equal and opposite reaction. That's not true. But Newton's 3rd law actually has many other little parts to it. Like for every impulse, there's an equal and opposite impulse. That's true too. Meaning that you can't touch something without being touched yourself, and the length of time that touch lasts is the same for both objects. That's why it involves impulse and therefore involves momentum. Ultimately, Newton's 3rd law is a statement about the limits of a system because it discusses how forces are both internal and external and determines where the boundaries of your system are. And that's what we're going to discuss a little bit in this problem. So it's a little bit bigger than our discussion from last year, those of you who had regular and honors physics and AP Physics 1, where we just talked about how forces come in pairs. It's a bigger discussion than that. But Newton's 3rd law is the action-reaction pair. What's really important that you take away is that the action-reaction pair represents 2 different objects. So although there is an equal and opposite force, these 2 forces act on different objects. And we're going to be very clear about what those objects are here in this particular example. So without further ado, I want to talk about the Atwood machine and how Newton's 3rd law applies to it. But I also want to make some caveats about the Atwood machine. For this Atwood machine, we're going to say this is M1 and this is M2. And then the pulley, of course, could have mass as well, MP, but we're going to, for the time being, really kind of focus that the pulley's mass is 0. And I have a couple of reasons why I want to do that, but I want to start out by recognizing that no matter what happens in this system, no matter how we observe it, no matter what is going to occur, like I don't know what's officially going to happen. I don't know whether M1 is going to go down or whether M2 is going to go down. I have an idea that whatever one is heavier is the one that's probably going to be move in a downward direction, while the lighter one's going to go in the upward direction. That makes the most sense to me, but we don't necessarily know ahead of time which is which. But most importantly, I expect somewhere in all of this that the inertia of the system is going to show up. And I would encourage you to start looking for this, especially in multi-body problems. In multi-body problems, you should see the sum of all of the inertia appear somewhere in your question. If you don't, you've made a mistake. This system can't accelerate without the entire inertia of the system playing a role. Now, for right now, that means the sum of M1 and M2. That is the inertia of the system. But in the future, it's going to be M1, M2, and somehow the inertia of the pulley as well. And so we should expect in any of these problems somewhere to be the inertia of the system. Now, that being said, I want to observe the forces that act in the system, and we're going to treat the system like anything else. In a multi-body system, the only difference in doing our work is that we have a net force set of relationships for each object in the system. Effectively, there's more than 2 objects in this system. I'd say there's probably 4 objects in this system. There's the 2 masses for sure, and I would hope that you guys would have identified those from last year. But there's also the pulley. It's an object in our system. And it being attached to the ceiling's a part of our system too. In fact, I'd go as far as to say that there might be a 5th object in this system, the Earth, since the Earth is a part of this system as well. There'd be no force of gravity without the Earth causing that. So our system tends to have limits and boundaries. We might be focused specifically on what happens to this one mass, but the motion of that mass is completely dependent on all of the factors of the system. So when we refer to the system, we need to make sure that our system takes into account all the interactions that can occur. So let's start by first recognizing that we don't know what direction the system is going to move, so we must choose a direction to call positive without knowing that the direction the system might move. So I tend to want you to focus that direction on the pulley. Meaning, do you think the pulley is going to move clockwise or counterclockwise? If we assume clockwise, then we're going to establish that this direction of rotation is positive, which suggests then that this direction will be positive and this direction will be positive. Now, I want to preface this statement that if you don't like the way I do this, there are alternatives. I believe in establishing a general direction for positive that is extended to all of the objects in my problem. The book does this a different way, and you are more than welcome to use the book's method if you want. This problem is about, I like it because it allows me to establish direction and then lets me interpret the answer according to direction. But the book does it different. The book would make you use everything. Up is positive for everything, down is negative for everything. And it has another method for how you establish what direction it's going to be like. So if you want to see an alternative, look at Knight's derivation of this. It's a little different than mine. But we establish direction starting here. Next, I want to start considering all the forces that are acting on each object in the system. And I want to begin that process by looking at the forces acting on M2. Name a force acting on M2. Sure, I think we all can agree there's going to be a gravitational force acting downwards on M2, equivalent to M2G. Now, there is an equal and opposite reactive force. That equal and opposite reactive force acts on the Earth and is pulling upwards on the Earth. And of course, the size of that force is still M2G, but it acts upwards on the Earth. We don't usually assume that the Earth is affected by these little tiny forces. The Earth has an incredible amount of inertia, and because of that, it doesn't have an acceleration that's worth mentioning here. I mean, technically, though, it does. You fall towards the Earth falls towards you. It's just that your chance of moving the Earth is pretty small. Now we need another force here. Another force acting on M2. What is it? Tension. Now, we have to decide how to draw this. In this part, I beg of you, be patient and careful. We indicated the positive direction, I hope, with the idea being that we think it's going to move in that direction. So I'm going to draw the tension force to be slightly larger than the weight. But I'm also going to call this tension 2 because it's attached to mass 2. There's a Newton's third law of force then that must act according to Newton's third law. So there needs to be an equal and opposite reactive force. The box is being pulled up on by the rope, so there's an equal and opposite downward force from the rope on, in this case, the pulley where it's attached. This is the Newton's third law reactive force. Now, this pulley does not do any kind of exchange of force for distance. It's a single pulley. So a single pulley tends to redirect force. That's what a single pulley tends to do. So that's why, we know the rope wraps around the pulley, redirecting this force. However, there's probably a tension on the other side of the pulley due to the presence of box 1. So let's go through and identify the forces acting on box 1. Anybody got one? What's that? Gravity. So we have gravity acting downwards, equivalent to M1G. And that means there's going to be an equal and opposite reactive force acting on the ground or the earth from box 1. Now, when I drew M1, I wasn't spending a lot of time being careful. If we think the system's going to accelerate so that the pulley goes clockwise, that probably suggests that I should draw M1G longer than M2G. Now, I also know there's going to be another tension. That tension is going to act on M1. It's going to be upwards, but I need to draw T1 so that it's less than M2G. Why? Because I think it's going to accelerate downwards. Now, the reactive force is going to be the downward force of T1 acting on the pulley. Now, interesting thing here, if our pulley has inertia, then T1 and T2 aren't the same. That would have to be true in order for the pulley to be turned by these tensions. They have to be unbalanced. If they are the same, the pulley can't be turned because the net torque would be 0. Now, we're not talking about torque yet, but I need to start getting you to think about the fact that the tension on either side of a pulley doesn't have to be the same. We tended to treat it the same last year, and we are going to for a little while now, but it doesn't have to be. Should the pulley have inertia, there will have to be unbalanced tensions here. But for this case, we are setting the pulley's mass to 0, which means it has no inertia, and under that circumstance, the tensions are all the same. So for right now, equal tensions all around. Now, if we are only going to be observing what happens to the two boxes, we have enough information to do so. But I also want to consider that there's an upward force here, the force on the bracket from the pulley. And I don't have a name for this. It's probably a normal force or a tension force, but I'm just going to put an F with a little B there. So it's a force from the bracket. There's a Newton's third law force here too. And that third law force will be the interaction of this force and the ceiling to where it's connected. Again, I don't know if that's really part of our problem or not. So, we've identified all the forces that act in the system. The thing about a multi-body system is understanding how the motion of one object in the system is related to the object of another part of the system. This one's really easy in that whatever acceleration this box has, this box should have the same acceleration. In fact, these boxes will share acceleration, displacement, velocity. As long as the cable connecting them doesn't stretch or break, they are locked in their motion. Now, just keep in mind, that does not have to be true. You can have situations where different parts of your system are moving at different speeds and different accelerations. These are convenient in that they have to move together, but I could just as easily have drawn one where they don't. So just be prepared that you need to figure out how the acceleration of one object might be related to the acceleration of the other. Okay? In this case, they're the same, which is good, because I want to analyze the system and find an expression for this acceleration. So let's handle that by talking about the left side first. We've decided that upwards is positive, so net force equals M2A. Obvious mistake that most students make starting this is not recognizing that you have to identify each of the masses separately here. You can't just put M here. And worse, when you start getting numbers, you got to make sure you put the right number there. But we're going to have T minus M2G equals M2A. There really is no point in taking a look at the X direction. These forces are all linear. They're all in one direction. It's pretty straightforward. On the other side, we're going to do something similar, except downwards is positive on the other side. So I get M1G minus tension equals M1A. Now, ultimately, you should have one or two force equations for every object in your system. So this one, I think we're only going to have one force equation for every object in our system, with the last one being FB equals 2 times T. The pulley's net force is 0. Now, for a problem like this, I'll remind you, the only thing forces can do is tell you an acceleration or a force. So looking at what I have here, I do have the capacity to probably figure out what the acceleration of our system is. Or I could figure out what the tension is. Let's take a look at the acceleration of the system. I think that's the most obvious question to ask. So we're going to move this, make it a little bit smaller, give us a little room to work. And I want to recognize that I can start with T equals M2G plus M2A. I'm just going to start the process of substitution. I've got two equations that have tension in it, two equations that have acceleration in it. Seems like eliminating the tension is probably the way to go. Once I've done that, I can do my substitution into here and get M1G minus M2G plus M2A equals M1A. I want to get the A's on the same side. So M1G minus M2G equals M1A plus M2A. Just a little algebra there. Now I will factor out the A because I need you to see something. When you have combined your equations and eliminated an internal force, tension is considered an internal force in this case because it acts in opposite directions to two parts of your problem. Once you've done that, you should be left with something that makes obvious sense. Let's see if you understand what I mean by obvious sense. The left side is the difference in two forces, the weight of one block and the weight of the other. That is net force. The right side has the inertia of the system, m1 plus m2, and the subsequent acceleration of the system. You should be able to clearly see that in any multi-body problem that you're given. In fact, I didn't really need to do all of this to jump to that point. Newton's second law states that the net force on the system has to equal the inertia of the system times its acceleration. I don't need all this fancy math to realize something is pulling down here, something's pulling down there. The difference between them is going to determine the net force on the system. How fast that system accelerates will depend on how big the total inertia of the system is. There should be some obviousness to your answer. Of course, I will expect you to go farther than this. I will expect you to be able to solve the problem for acceleration or tension or whatever else. And in this case, I expect to be able to see that the acceleration is going to be, and I have a reason why I want you to write it this way. I'm going to do m1 minus m2 over m1 plus m2 times g. It's traditional to collect the masses out front, mostly so that you can see how the masses interact to produce your answer. Like, there should be some obvious stuff here. If the masses are the same, the system doesn't accelerate. That's obvious, that's here. But it also should tell you that if one mass is much bigger than another, you should get some extreme circumstances for what happens. Like, if mass 2 is bigger than mass 1, the acceleration is negative, meaning it will go the other direction. All of those kinds of things are obvious tests you should do whenever you get an expressive answer like this, to see if they make sense. All right, that is a straightforward Atwood machine question. Are you going to be faced with one like this? No, it'll be harder than this. This is just getting us started. Like, one of the first ones you might see is going to have another box hung here. Doesn't change it very much, but you know, it was on the AP exam. Asks about the tension in here. So this is a triple body problem. Not much different. They all accelerate the same. But we're going to see a couple of these. So again, take a look at what we did in fourth period. It was the modified Atwood machine. That's a block on a table, block hanging off the edge. And seventh period, we're going to take a look at either the train question or like 3 boxes in a row, and there's a net force on one side of the system. We're going to look at those kinds of multi-body questions. All right, I'm going to hit the pause button. That one, that plus the pulley problem, which of course you'll notice in the pulley problem, we also have this point where we see the total mass of the system show up. So give me a second to first make me the spotlight for everybody, because I have to be the star. And let her talk really loud.
This meeting is being recorded.
All right, so this will be the third of the 3, and again, this should be the end. We are really trying to introduce and drive home the concept of Newton's third law. And let's just get a quick reminder in case it didn't get brought up in class yesterday, that Newton's third law is the action-reaction law. It does not state that for every action there's an equal and opposite reaction. That is not what it says. It says for every force there's an equal and opposite reactive force. That's what it says. And it's incredibly important that we understand the difference. For every force there's an equal and opposite reactive force. It doesn't say that for every action there's equal and opposite reaction. And I don't want you to think of it that way, because it makes it sound like actions instead of forces. For every force there's an equal and opposite reactive force. This means that all forces come in pairs. And those force pairs are of the same magnitude but opposite direction and act on different objects. And we're going to talk specifically about that in this problem. So let's define a few characteristics of this problem. Let's name this mass 1, mass 2, and mass 3. And through the course of this question, we are going to try and identify all of the reactive forces, both inside the system and outside the system. Let me help you clarify that. Newton's third law is really about defining the boundaries of a system. It's where the system, ends, and we can focus on the part of the problem that's important. So when we start looking for what are called internal forces, these are forces that exist inside the system, where both objects that are experiencing a Newton's third law pair of forces are part of the system, as opposed to external parts of the system. For example, let's look at the forces acting on box 3. Okay, box 3. So name a force acting on box 3. Just shout one out. I can't see your hands in the dark. All right, so gravity is a force acting on box 3. I think we can all agree a downward arrow makes sense. M3 times G is the size of that. The reactive force. So we were talking about what, the weight? Is that right? Yeah. Anybody even remember? So there is a Newton's third law force here, and the Newton's third law force is going to be the force on the Earth from this box. Now, do you think that force really matters? Are we going to potentially have the Earth as part of our system? Is the force of the box on the Earth going to move the Earth enough to matter as part of our problem? So generally the answer is no. We don't have to include that interaction between the box and the Earth because it really isn't going to have enough of an impact on the Earth to make any difference. So when we evaluate the Newton's third law forces, we just have to take into account forces that we think are probably going to influence our system. So that's where we want to focus. So weight is one force that acts on the box. Another force that acts on the box is normal force. Now be careful. There's a lot of normal forces in this problem, a lot of normal forces. So as we start to name the forces, we might want to be careful to pick names that we are able to utilize and understand what they mean. For example, I'm going to put normal force from the ground, because there's another normal force acting on box 3, isn't there? This counts as a surface, so there is a normal force this way. This is a normal force on box 3 from box 2. So I'm going to put it as normal force 32. On 3 from 2. You follow along with all that? Now, let's just, so that you guys don't freak out too much, let's make this frictionless. Because I don't want to have to also put in friction for this right now. I think this is going to be enough on our plates with the way today's going. Fair enough? Yay. Okay, so we're going to go over to box number 2. Box number 2, I think we can all agree, has weight. And I made box 2 look bigger, so I'm going to make its weight a little bit longer. Good enough? Now, there's also going to be a normal force in the ground. Pretty sure that's going to be balanced. I'm just going to put NG. These two NGs aren't the same. I just need to keep that in mind. If you want, this is NG3, this is NG2. You see how complicated this is going to get, right? So let's just, let's keep going with this. And here's where I have this surface. We already used it once. That was the normal force on box 3 from box 2, which means there's got to be an equal and opposite force here. Normal force on box 2 from box 3. Those two forces form a Newton's third law pair. That is the action-reaction pair. Box 2 pushes on box 3, but box 3 then also pushes on box 2. Got it? But there's also normal force on box 2 from box 1. I think that's it. Which brings us to our last box. Box 1. Smallest box, smallest weight. Normal force from the ground? Sure. Normal force from the ground on box 1. Now, I have to be consistent here. There's got to be a Newton's third law pair in this direction. Normal force on box 1 from box 2. That is a Newton's third law pair. So this one and this one are equal but opposite. But there's also this pushing force, which I'm just going to call big F, because today has just been a big F. So we have identified all the forces that act on each of the individual objects in our system. This is a train problem. This is a row of boxes problem. These problems look like this, with all these individual normal forces, these third law forces all kind of sprinkled throughout the problem. The biggest thing to remember about all of these problems, including the other two you haven't seen today, is that all of these problems, at some point or another, we should expect to see the total inertia of the system show up. I am expecting that the total inertia of the system is going to be within this problem somewhere. That the whole thing is going to hinge on the fact that at some point or another, the inertia of the system will decide how much this system responds to the applied force. So I don't know when to expect that, but I do expect at some point in the future here. So we're ready to talk about solving this question, but this was just the setup of the question. Can I go on? I don't even know if that's a yes or a no. You're the best. Here's the thing. You'll notice that we have not done anything different yet except for the inclusion of these third law forces. You see that we are drawing a free body diagram. We are trying to identify the forces as they act, which meant that we are looking for any points of contact and any fundamental force, any cables, or any friction. We are still doing the same set of steps. And I'm going to continue that set of steps in saying that our next job then is to employ Newton's laws, which would be to consider if this is a first law problem or a second law problem. And it might be hard to judge it here. It is not hard to judge it there. Wouldn't you agree? So I think this is a second law problem. More importantly, I don't think it's possible for box 3 to accelerate to the right without box 2 being in contact with it. You guys follow that idea? That it's box 2 that pushes box 3, and it's box 1 that pushes box 2. So it's likely that all 3 boxes will have the same acceleration. The only way that's not true is if one of the boxes is getting crushed. Right? Box 1 could accelerate more than box 3, but that means box 2 is collapsing. Or box 1 is entering box 2. Either way, I don't really want to go down that line of reasoning, do you? We assume that all of these boxes, unless we're told differently, are going to travel together. That's important. That means that all of these sets are going to have a net force equals ma, where A will be the same for all of them. That's a critical piece of information. Now, because there's no friction, I see no reason to worry about the y direction. Is that good for you guys? Getting no feedback. None at all. I have no idea. I know, it's like super dark in here. So, I'm going to start by looking at the last box. Net force on M3. Because there's only one. N32 equals M3A. We good? That's it. That's all there to do. And that is the net force in the x direction. So now I'm going to go over to the next box, the middle one. Net force on that box equals M2A. There are 2 forces that act on this box. There's N21 minus N23 equals M2A. Still okay? So nothing to do. That's it. That's all I can do. I don't know what any of those normal forces are. But I can go to the last one. Net force on box 1 equals M1A. What's that going to be? Well, it's going to be that pushing force, the big F, minus N12 equals M1A. Really, Mr. Shelton, this just looks like a mess. What's the point of doing all this? Well, I'll tell you the point of doing all this. This and this are the same size.
There's a huge delay.
There's what?
A delay. Like your camera doesn't is a delay, but the iPad is really got a delay.
Well, you're right. This and this are also equal. No wonder everything's so funky.
Teachers and students, thank you.
It is now. All right, so the thing about these problems with anything that has Newton's third law is you're going to be doing a whole bunch of substitution because all of these forces are the same size. So the first thing I'll point out, which I have to say, and then not really, I got to not say it because it's so delayed apparently, is that you can substitute in for the normal force what we have in that last function. I said that the normal force is equal to M3A, so I did the substitution. That got rid of one of the normal forces between the two. And now what do I have? I have a new function that has one less normal force in it. You follow that? And I can do this again now because I will point out that I have the normal force for 2 on 1, that's got to be equal to the normal force 1 on 2. I factored the delay into the way I'm talking. Did you notice? It's working out okay. People at home have no idea, but I told Sam's joining us now. What's the point, Sam? Way to go. Way to slide in here at the very end. Act like you've been here the whole time. So I'm going to do this last substitution. Be careful about your negative signs and stuff because it's really easy to not be paying attention and screw up one of the negative signs. I have that negative there. Need to make sure I apply it to everything. So, put the parentheses there to remind you. The negative signs that we are inserting is the fact that we already know that these forces are opposite, but we know they are the same size. So we put the negative sign because of the direction they point. But ultimately, we kind of know where it's going in the problem. So I'm at the last part here. All I got to do is solve for the force. And what I'm going to get here, I hope, isn't a huge surprise, even though I'm done writing it and it's not done putting it on the screen. If we look at the system from the standpoint of a big system, move that over here. If I take this relationship and just do a little bit of, distribution, factor out the A, what you should see is that although there are a lot of forces that acted in the system, in the overall scheme of the system, there's the unbalanced force, that was the big pushing force, the one that's all the way up there on the left, that was acting on the whole thing. It's equal to the entire mass of the system, the inertia of the system. That's all of the masses, and therefore the acceleration of the system is going to be based on the entire inertia of the system. And that's what we see here. We have the sum of all the masses, it's right there in the middle. This acceleration applied to all of them, and this force was the external force on the system. Now, what it really suggested is that we had our most basic problem that we had at the very start of your, first time taking physics years ago, back in the 8th grade, when you had physical science, that there was really just one big box that was experiencing one big F force, and the box had a mass of M1 plus M2 plus M3. That's really what's being said here. That the applied force on the side didn't know it was pushing on 3 boxes. It just knew I was pushing on something that had the inertia of those 3 boxes. And the system responded with a net acceleration that was based on that net force. But by breaking it up into these pieces, we also now have a way of figuring out what the forces are in between the boxes. This tells us how much force is on an individual box, and will that box be able to withstand it? If you guys have ever been working in any kind of store, you know that every time you unbox a case of whatever, outside that box is something about the crush strength of the box. How many can you stack high on a pallet? Something like that, to let the people know that they can only take so much force before they will crush. Well, that's the interaction of these 2 forces. If we look at where those 2 forces actually act on M2, those 2 forces don't act from its center. Those 2 forces act on the outside of M2. There is N21 here and N23 here. They're acting to crush this box. Now, just so you know, big picture, we could have started this whole problem doing this, treating it like one object. The moment we knew the whole thing accelerated at the same rate, we could have skipped all of this algebra and found the acceleration right away. It would have been the force divided by the sum of the masses. And I would encourage you to do that. Get the acceleration the moment you need it. But I wanted to make sure you saw the full derivation of what it means to have these boxes kind of lined up. So that is the 3-body problem. That is the multi-body boxes in a row problem. It is the same as the train problem. And now